Right, we better get on with today, otherwise we're going to run out of time. So, this is notionally the second to last lecture, but in fact there's a secret hidden lecture at the end without any notes, where I just go through some op-amp stuff, which will start today. After the 17th lecture, they're mine, get away. Someone find this man some notes. They're up, must be up the back somewhere. That's what you get for turning up late. After the last lecture, there will be another lecture in which I go through last year's exam, which I do all the questions. Just so you, if I haven't managed to force it down your throat enough that you have to do the questions, you will see me doing some questions and then you'll believe. Right, so just before Easter, we had an example of the calculation of Circuit 2's DC conditions, and if you're unhappy with it, then there are 3 videos. Oh, come on. Now, you see, this is my fault because I gave out the notes too early and people came in afterwards. Right, so if you're feeling unhappy about working out the DC conditions, there are those extended videos which show you how to do it. And then we talked a bit about biasing circuits, and I said there's almost always some compromise. And then we looked at coupling, that's to say using capacitors to form a virtual short circuit for AC signals and an open circuit for DC voltages, in order that we could get signals in and out of a circuit or an amplifier without upsetting the DC conditions. And then we said that decoupling was the removal of signals where we didn't want them. And then I talked a bit about small signal models for bipolars and JFETs, and we looked at how all transistors, all 3 terminal amplifiers are actually transconductance amplifiers, sort of boiled down a bit. You can think of the bipolar transistor as a current amplifier, but sometimes it's helpful to do that, but most of the time I prefer not to. And, well, we didn't derive, I stated some key relationships, and you can remember them as articles of faith if you like. So today I want to talk a bit more about how there are some notes in this corner over here. No, not the back. Nice. You will need to watch the video to understand that. Yep.
These are like 14 notes.
Are they?
Yeah, they're wrong notes.
Ah, but they're corrected, because I made 2 blinding errors. What's happened is, I came in last night to print the notes and found that I'd left my U-card at home because I came from London. So I left them on an administrator's desk at about 10 o'clock and said, can you copy these for 10 AM? And the photocopy was jammed, unfortunately. I will bring you the right notes if you haven't got... So there's 2 sets of notes floating around. One is 14 with corrections and one is 15. And I assumed I had all 15 in my hand. So if you haven't got the right notes, don't panic, I'll bring plenty tomorrow, with a bit of luck. So, this is good because it means I can give you biscuits for really answering questions as opposed to looking at the next slide. I should do it more often. So today it's feedback in amplifiers without emitter decoupling, and then the feedback of signals in amplifiers with emitter decoupling, and then I want to talk a bit about how the feedback works, because it's not really intuitive unless you think about things in the right order. You can get a bit bound up. It's like putting in an equation in Excel, cell A1, and then writing in B1 an equation that relies on A1's answer, which gives you A1, and it just sits there going round and round. Eventually it goes, I can't do this. Well, that's a bit like how the feedback is, so we need to talk about it a bit to see what should happen. And then I want to go back to small signals for a bit, just to round it off, and then we'll start talking about op-amps. So this is the feedback of signals in amplifiers without emitter decoupling. So without decoupling means no capacitor just there. So the order I like to look at this in, which is not the only way, but it's the one that I prefer, is to say there is a voltage on this node which is passed in by virtue of Vin being there, and this voltage perturbs VBE somewhat. We'll assume at the moment that there's no current flowing down here, in order that there should be no voltage across RE, which isn't really true, but it helps. And this perturbation is making up all of VBE. So this is, blue is with respect to ground, green is across a resistor, say, so those two, and red is current. So this perturbation across VBE, which I'm taking to be the blue one at the minute, causes a current to flow in the collector, which is the red one, by virtue of transistor action. And this current flows through the transistor's collector and into the emitter and then out again and through RE, causing this green voltage to appear across RE. And this voltage subtracts from this one to leave only a very small amount actually across VBE. So the effect of not decoupling RE is that the voltage across RE subtracts from the voltage at the base to leave only a little bit for VBE. And that is what reduces the gain of the transistor. Or rather, the gain of the transistor doesn't change, it's just the apparent size of the input signal has been reduced. Want to hear that again? Stunned into silence. Such is the power of electronics. So, we put there's a voltage source here, and we put a voltage in the base, and we'll assume that we've just switched the transistor on, and in an infinitely small amount of time that's we're looking at, nothing interesting has happened to the transistor yet, but we're worried about what will happen to the signal when it goes in. So this is the signal we're putting in, and while there is no collector current flowing, which isn't really true, but we have to suspend our disbelief for a bit, otherwise we'll end up in the loop. While there is no collector current flowing, all of this voltage turns up across VBE because V is 0. And this voltage causes the transistor to be slightly turned on and slightly turned off and slightly turned on and slightly turned off and so on. And that slightly turned on and off is causes a change in the collector current here, which causes a change in VRL, but that doesn't matter. It also flows through the transistor out of the emitter and through RE, and it causes a voltage to appear across RE, which acts to, because we have a loop here, we've got VR1 is essentially that, and that must be equal to VBE plus VE. Now if VE is now this, and this is all we've got to go on, VBE must be shrinking in order to make all the numbers match. So the effect of not making this signal go away across RE means that VBE must be reduced by the subtraction of that from that. If you're not happy, it's in a couple of slides' time as well, written out. So what happens if we do decouple it? If we were to put a capacitor across RE, what would happen? Well, I've put some signal currents in now, so signals are small, which is why they're lowercase, and quiescent conditions are big, which is why they're uppercase, or DC conditions. So in this case, same situation applies. We've got a signal that we put onto the base, which is going to drive our transistor, and in the first instance, let's assume that there is no current. So all of this voltage falls across VBE, causes this current to flow in the collector, which flows into the emitter, but then the signal has a choice. Now, the DC conditions must go through RE. Why is that? Ah, biscuits. Was that, what was the answer? Capacitor will be an open circuit. I think you both get biscuits. Well, you don't pass one as well. Don't want a biscuit? So, just in case you didn't hear it, the capacitor is an open circuit as far as the DC is concerned. So, from DC's point of view, this capacitor does not form a path, is not a pathway that it can flow through. So it must take RE. The signal, on the other hand, sees a reactance, which is what equation? Or impedance, if you prefer. XC is 1 over 2 pi FC. Is this news? Yeah, okay. Well, if it is, panic. Right. So the signal will take this route, and there'll be a signal current which is sinusoidal, but IE will be a DC current. And if you wanted to draw it on a graph, it would just be a straight line. All these graphs are with time on it on x-axis and amplitude on y-axis. So the voltage that appears across the C2RE parallel combination due to the signal current is now very small, and it's the signal current times the impedance of C2 at the frequency of interest. Now, I haven't bothered to define a frequency, but there would be one, and you would know what it was if you were working these things out, sort of for real. So that means that having reduced the signal voltage across the REC2 parallel combination, we've now got almost all of VB the voltage across R1, which is the voltage at the base, so I'll call it VB, appearing as VBE. So the transistor's gain appears not to be reduced anymore. So the transistor's gain doesn't actually change. It's the circuit that surrounds it that affects it. And it's the feeding back of the current flowing through the load, through the emitter resistor, producing a voltage across the emitter, subtracting from the base node voltage, which makes VB appear smaller. Transistor still has the same gain, it's just amplifying a smaller signal to start with. Similar arguments apply to the decoupling in circuit 2 of the resistor which feeds back from the collector to the base. But I'm not going to go through it. It's in that handwritten handout. I've got another handout which is nicely typed up, but it's not quite ready, so I'll bring it tomorrow. So how the feedback operates, this is what I've just said, but written out. And you'll get this tomorrow, and if you can't wait that long, you can get it online. So a signal voltage is impressed on the base with respect to ground, so that's V in on the prior slide, causing a voltage to appear across the base emitter junction. That's that one there, which in turn causes a current in the collector, which is a red collector current, and because we're saying IB is 0, it also flows in the emitter. The emitter resistor drops a voltage, which is I times RE, which is that bit there. And since VR1 is fixed by Vs and the ratio of R1 and R2, VBE must reduce. All I've said there is that the ratio of these two fixes what this voltage ought to be with Vs. So there's a potential divider here. So this voltage is fixed, and subtracting this from that is the only thing we can do to work out what VB is. So the bigger this gets, the more is subtracted from that, so the smaller that must become. So the feedback for DC for signals is undesirable because it reduces our gain. And usually one of the things we want from an amplifier is nice big gain and plenty of bandwidth and lots of other things besides. But for the purposes of this argument, gain is what we're interested in. So the feedback is undesirable as far as the signals are concerned, and we remove it by decoupling the emitter resistor. That's to say, you put a capacitor around it, which has got a very low impedance at the frequency we're interested in. And ZE is RE. Those two slashes are in parallel with, and it's fine for you to use that to mean in parallel, as if it was another mathematical symbol, like addition, subtraction, modulus, whatever you want, licets, anything. No? No, never mind. We'll go read about them. They're really important to do with phases and how Schrodinger's equations derive. Anyway, so where CE is large enough to dominate ZE at all frequencies of interest, the feedback for DC conditions is desirable. And that's because it stabilises the operating point. So there is a current which flows from collector to emitter with a little bit of contribution from base, which is DC, and that sets the operating point, and it deals with the graph that I drew over here about a month ago now, where I said there's this much space available for all the signals, and there's this much space required for VB, and VE must be below VB by 0.7 and all that, and power supply is right at the top, and you have to apportion up your voltages accordingly. This is the quiescent current that sets up all those voltages for us. Well, most of them. And we have to make sure that there is sufficient feedback at DC to keep stability in those values, because let's just say I had 2 milliamps as big IC, and there were no signals at all. Then we'd have some VBE here, which was necessary to make that 2 milliamps flow, and we'd work out what that VBE was, either with a graph or by a set of equations or whatever, and we'd produce an R2 and an R1, which gave us the right value by working out potential divider of Vs, and then that current would flow, and we'd be happy. And then the transistor would get a bit hotter because the current was flowing, and that would mean that the VBE that was needed to cause that current to flow would be slightly smaller than it was before, which would mean the current would get bigger, which would mean that the transistor would get hotter, which would mean that more current would flow, which would mean that the VBE needed to keep that current flowing would be smaller still, which means that more current would flow, which means the transistor would get hotter, and if I keep going, my head might explode. Much like the transistor. This will be thermal runaway. And we can escape from that by putting RE in, because then we can say, well, I would choose a value, VE, across RE, say a volt or two, and I will make R1 a couple of volts, and I'll know that VB is going to be 0.7. So if I said that was 1.3 and that should be 0.7, this will be 2 across there. If I did that, I could say, well, this will cause a certain current to flow, which I've decided upon. And if the transistor gets a bit hotter, a bigger current will flow, and a bigger voltage will be dropped across VE. But this point is fixed. So all that can happen is VE has to get a bit smaller, which turns off the transistor a bit, which causes less current to flow, which means it cools down somewhat. And all this is happening all the time, and we're stabilising the operating point. It's the same set of arguments that means that the amplification of signals is not as big when we've not decoupled RE. But because the capacitor only decouples RE for signals, you can't decouple the DC. Okay, there are ways, but not with capacitors. We can use RE to keep our DC conditions nice and stable, and we can use C2 on this diagram to get out of the fact that we'll reduce the gain. So RE is important, and we can't just take it away. We can take it away in circuit 2 because there's another mechanism of feedback. So the feedback for DC conditions is desirable because it stabilises the operating point, and that's what I've just described. The capacitive decoupling does not affect the DC conditions because, as you want a biscuit for, the decoupling capacitor looks like an open circuit at DC. That's to say, at DC, ZE and RE are equal in value. That's the last thing I've got to say about those two circuits. Everything that follows is to do with what happens to signals when they get into the circuit. So once we've managed to couple the signals in, how will the signals experience the circuit? And if you've been reading the handouts that I've given out before Easter, then we can go back to small signal equivalent circuits, and these are the same sort of small signal equivalent circuits that we were talking about when we were discussing diodes just before and after Christmas. And we were saying that there would be a 0.7 volt voltage source with a little resistor, RS, in series with it. And we said the value of that little resistor depended on how much DC current was flowing through the diode. And I drew a curve and I drew a tangent to the curve, and I said that RS varied according to the tangent of the curve, and so on and so forth. And then later on we did the same thing with transfer characteristics and transistors, where we had VB on X and IC on Y. And I said, well, the GM is DIC by dVB, and you put a tangent on it. Broadly the same sort of thing, just slightly rejigged. So now we need to draw some circuit diagrams of what the signal sees. And that's the key thing about figuring them out, is thinking as if you are the signal. So when I write the lecture notes, I try to remember what it's like to be on that side of the bench. And when you work out the small signal circuit diagrams, you have to try and remember what it was like when you were a signal. That's right, eh? So we have to worry about how the signal sees the circuit. And there are several consequences of this consideration. And in principle, you just remember these 3 points and you apply them, and the right answer drops out in front of you. But that trivialises something which is not necessarily easy when you first try it, so don't panic if it's not always obvious. All the DC voltages and power supplies and so forth are replaced by their Thevenin equivalent impedance, which is 0 ohms. all the DC current sources are replaced by their Norton equivalent impedance, which is infinite ohms. And in small signal problems, in this course at least, capacitors are treated as if they're open circuits to DC and short circuits to AC. So you don't have to worry about what the impedance of the capacitor will be at 1 kilohertz or 50 hertz or any of that. You can just go short at all frequencies from a couple of microhertz to light and beyond. So with these three things in mind, you may recognise the first two actually because they come along in superposition as well. With these three things in mind, the transistor is replaced terminal for terminal by its small signal model. So this is circuit number 2 with RE decoupled. And that's what it looks like in small signal terms. So looking at point number 1, C1 is short circuited, so it's just a wire. Point 2, C2 looks like a short circuit, so RE disappears because RE is now in parallel with wire. So the parallel combination of RE and the wire is 0 ohms, which is the resistance of the wire. And VS, VS looks like a connection to the ground from the signal's point of view, because this one isn't quite so clear. But if I had an interactive whiteboard, if I had a battery down here, like that, imaginary battery, it would be replaced by its Thevenin resistance. And if it was an ideal battery, that would be 0 ohms. So what I'd actually have is a line connecting the VS line down to the ground. Or if you prefer, I'd have a little resistor in there with a value of 0. So that's how VS looks like to ground. It's the same set of arguments which are used in the construction project for why R15 and R16 look like they're in parallel when you're calculating the Q value for your second stage, where you've got that cascade of a JFET and a bipolar. And when you do all the calculations, R15 is biasing some push-pull stage from the supply to the base, and then there's another resistor from the base to the ground. And when you do all the calculations, they turn up in parallel, and all you do is double the value worked out, because then they're both in parallel and it splits. That is the reason for they look like in parallel, because as far as the signal's concerned, it looks up through the resistor into the power supply and sees the short circuit into the ground. And that's how they become in parallel. So what about the big chunk in the middle? The transistor's gone, and it's now been replaced by a small signal resistance between the base and the emitter. That's RBE. That one there. Nearly got you. It was on the wall. Obviously we have insurance against that sort of thing. And this laser is not powerful enough to harm any of you, maybe. Except in my office where it's a lightsaber. And this is the controlled current source, which represents the collector to emitter arrangement. And this is controlled by the small signal transconductance GM and the small signal voltage between the base and the emitter. So that's what we need to do, and we can just drop that in. So this is the base, that's the collector, and that's the emitter. And you scrub out your standard transistor symbol, which is the one with a little symbol on the emitter, and you know the one. That one there goes away and gets replaced by all this stuff in there. All the other components just stay in their same position. So R1 connects the collector to the emitter in the prior circuit, and it connects collects the base in the prior circuit, and it connects the collector to the base in this circuit as well. But this isn't very nice to start drawing loops and solving no voltage and that sort of thing. So we can redraw it like that. It's the same thing, just neatened up a bit. So the important thing to remember is that the small signal equivalent circuit is not the same for every circuit. The transistory bit is, but the stuff that surrounds it will be different. So there is no logic to learning a series of small signal circuits, because you've no idea what you're going to come up against, either in some sort of fabricated exam situation, which isn't very realistic of modern engineering, or when you actually have to do some real engineering. So there is no point in remembering them. The trick is to figure out what you need to do to the circuit to turn it into the small signal model. And when you know the process, you'll be able to do it for any circuit, however complicated, however many transistors, whatever. So we've got this small signal circuit, and the one thing that you ought to, well, maybe you won't notice because it's not necessarily obvious, but all of the components in this circuit are linear. That is to say, they all obey relationships between voltage and current, which are not exponential or square law or logarithms or anything funny. It's all Ohm's law. In fact, it's all Ohm's law. And that's important because what we've secretly done without saying so is linearised the circuit. That's to say we've removed all the exponentials and whatnot and replaced them with a straight line version based on the point on which we were at the exponential. So when we draw, dare I wrestle with the projector screen. When we're drawing this graph, this is VBE. Notice this is big VBE and this is big IC. And we had that sort of shape, and this is IC is equal to IS, or IC0 actually is what I usually call it. E to the Q VBE from KT minus 1. And we'd say, alright, well, I'm going to choose a milliamp for the sake of argument, and then I'll be drawing a line up there, and the DIC by dVBE at this point, so drawn across those two, will be my GM. So this will be my small signal parameter, and if I was to move this operating point to up here, I'd get a different piece of chalk if I'm lucky. And I'd have a new line slope with a new gradient and a new GM. That is the relationship between the large and the small signals. That diagram and an explanation in words. Here we go to the pub. I beat you. Right. I don't see what's wrong with the little thing down there that I can tie it off on. That would definitely work and is totally under my control, but there we are. So that linearisation is what's causing this circuit not to have any exponentials or anything. It's just Ohm's law. And Ohm's law lives with straight lines. So once we've got to the small signal circuit, we can assess some parameters of our transistor, or our transistor circuit, because it's the transistor and the circuit act together. So the first thing we might like to ask is, what's your gain?
Can you put the screen back on?
I like it to be a challenge, I think. Yes, I can put the screen back on. So I don't mean to sit here and deride these, it's a bit of a pain to do it. It's in the handwritten handout with very, very nearly the same nomenclature, but this nomenclature matches the circuit that's further up these slides. So you'd sum the currents at the collector. Summing currents at the collector is lecturer speak for applying nodal analysis. So you do VC minus VE upon RL, which is that voltage there, and then VC minus VB upon R1, which is that voltage there. So what we're doing is, all of these things are currents, because they're volts divided by ohms, which is amps. So what I'm doing is I'm working out the current that leaves down this pathway, I'm working out the current that leaves down that pathway, and then down that pathway. And then I'll have an equation for all the currents that come and go from this node, which is the first step of nodal analysis. Nodal analysis is a friendly thing, yeah? Good. If it's not, panic. And then we do the same thing for the base. So we do Vs minus Vb upon Rs, which is current in Rs. And then we do Vc minus Vb upon R, which is current in R1. Then we've got Vb upon R2 and Vb upon Rb. The reason you don't have Vb minus something is the other thing. There's secretly a minus 0 just there and a minus 0 just there. But I've chosen not to write it because I don't think we really need it. And you can rejig 1 in terms of Vb and it'll give you equation 3. And if GMR1 is much, much bigger than 1, which is almost always true, because R1 is usually quite big, and GM is usually sort of 0.03 up to about 0.5, depends, you get Vc upon GMR1 parallel with RL. If you feel unhappy about how this is dealt with, either set R1 really big this evening and see what happens, or if you're feeling really brave, apply L'Hopital's rule and see what happens when R1 goes to infinity. So, as we transpose equation 1 into equation 3, we can transpose equation 2 into equation 4, and what I've done here is I've solved it for Vb. And I've left all the 1-overs because they're really just conductances now. And that expands, if you want to expand it, into a term in Vs, which is the first term on the left, which is Vs times a load of stuff in parallel on Rs, and Vc, which is our output voltage, because it's the voltage swing on the collector, times a load of stuff as well. And we'd have to use 5 and 3 to eliminate Vb. So eliminating Vb and transposing to get Vc upon Vs, which is the output voltage divided by the input voltage, which is a measure of gain, you end up with equation 6. If you dig around in the videos, I do this, the extended videos, to show how it's done. Or do I? No, I don't do this. I do it for the DC conditions. This one's for you on your own then. So the important thing about this result is that it tells us how the small signal voltage gain depends on the circuit and on the transistor parameters. That's to say, I can look at this equation, and if I wanted to, I could put some numbers in, and that'd be all right. But what I could also do is say, well, what should happen if R1 became really, really big? And I can look at the equation and say, well, this term's going to become really big, this term's going to be insignificant, and the circuit becomes slightly different, or a certain set of things will happen. In fact, in this case, if the term in R1 in the denominator is much, much smaller than 1, the gain is controlled by the resistors R1 and Rs. That's to say, if all this stuff here becomes quite insignificant, then the gain of this circuit is controlled by R1 and Rs, which is really handy, because we have total control over what R1 and Rs are. We can choose them, pick some values out of the drawer, and get a gain that we know what it will be. Won't matter what transistor goes in there. That's quite crucial. So the feedback that was caused by R1 in this circuit can be removed by making it infinitely large. If we go back to the small signal model, we can see that there's a signal on the collector, which is our output, and there's a signal on the base, and there must be some current that flows down this pathway, and that's a current that feeds back the collector signal to the base, and it acts to make the base signal smaller than it would otherwise be, and that means the transistor ends up amplifying a smaller signal, which yields a smaller result. So this is another kind of feedback, and we can ask what will happen if that feedback is taken away by making R1 really, really huge. So R1 disappears from all the parallel combinations in 6 to yield 7, and since R1 is very large, the R1 upon GMRL2 parallel RB parallel S dominates. So this is what I'm saying is that because R1's really big now, it's much, much bigger than 1. So this is the bit that becomes important, and this is insignificant. And that means that we can reduce equation 7 into this bit here. So the 1's disappeared, that's what's really happened. And if you rejig this, you end up with what I've got as 8 over there. And this is reasonably interesting as well, because we've got something to do with the transistor, which is GMRL, and a potential divider of the input. This is on the input, that's on the input, that's on the input, that's on the input. In fact, if we go back and have a look at the circuit, we've got RS in series with R2 in parallel with RBE. And if we look at the equation, we've got, this is a potential divider of RS on its own and R2 parallel RBE. So that is where that bit comes from in the circuit. So the circuit gain is now dependent on the transistor parameters. That's to say it depends, the circuit gain will change as our quiescent point changes. So if I was to move from the white line to the purple line, I'd end up with a change in gain. Whereas in the prior situation, it wouldn't matter whether I was at the white dot or the purple dot. It wouldn't make any difference. I'd have broadly the same set small signal parameters. Well, the circuit's reaction to small signal would be the same. The parameters would change. So what we're saying here is that the negative feedback effect of R1 has been taken away. So in removing R1, we changed the circuit from the small signal equivalent of circuit 2 to circuit 1 in the two circuits that we have. And R1 in circuit 1 is necessary for the correct bias in the transistor appears in parallel with R2 in the small signal model. And adjusting the value of R1 in circuit 1 will change the effective value of R2 as they appear in parallel. That doesn't change the small signal diagram. Each circuit shape produces its own result for gain and other performance measures. So you could work out the input impedance, which would be RB in parallel with R2 in parallel with R1 for type 1 for circuit number 1, and for circuit number 2 it would be slightly more complicated, but you could work it out. You can work out the impedance looking into the collector, which will be the impedance looking into the controlled current source in parallel with the impedance of the resistor RL, and you do that by driving a test current in there and measuring the voltage that, when I say measuring, I mean working out the voltage that appears as a result. And you can work out the power gain and lots of other things you want. You can choose any parameter of interest. So there is no point in learning that small signal model. It's just an example. And there is no point in learning the derivation that follows, because that derivation is based on the example. And that is somewhat more involved than any question I might ask you. But that kind of analysis is what a decent circuit designer will be doing when they're deciding on a circuit. And then they'll start doing other things like deciding if they can take away certain components or make it cheaper somehow, and they'll worry about the power dissipation, and they'll see if they can make it cheaper and not affect the gain or bandwidth. There will be lots and lots of different forces acting on their choices, and it is their job to balance all those things and get the best outcome they can within those constraints. So it's really just an example. For 5 minutes we'll start talking about op-amps. An operational amplifier is an integrated circuit. That's to say it's a chip with more than one transistor on it. And it's usually between 10 and about 50 in most commercial op-amps that are around today. And it implements a certain set of functionality, which we'll discuss. And it's often called an analog building block because it produces, or you can use it to produce various mathematical functions, addition, subtraction, multiplication, squaring, logging, derivative and integral, and that sort of thing. You can make an analog computer from one if you wanted to. And op-amps have been around since about 1930, and originally they were made from valves and were big and heavy and very power hungry. Some of their key characteristics are that they should have differential inputs. So it should have 2 inputs, and its job is to subtract one from the other. That's to say, it takes the difference. It should have a very high input resistance, because we don't want our nice analog building block to draw any current from the thing that we're driving it with. And it should have very low output resistance as well, because it ought to be able to drive anything that we desire. Now if you think back to that lecture I gave about ideal amplifiers, this sounds very much like an ideal amplifier because it has all the nice characteristics. And it should have enormous gain. And what we'll do is we'll throw some of that gain away in order to increase certain parameters of our circuit that we find desirable. So loads and loads of gain. And these are some typical figures. Op-amps are designed to be used with feedback, so we need to talk about feedback a bit more thoroughly than we have. We discussed some feedback in Circuit 1 and Circuit 2, but we never really talked about how feedback is sort of dealt with mathematically. We just looked at the voltages and decided what ought to happen. So there is a whole field of study of feedback, and it started quite a long time ago, but other than some mechanical feedback systems, the key things were done in 1925 through 1930, including a lot of work by a fellow called Nyquist, who has a stability theorem named after him. He also worked on the coding of fax machines and a load of other stuff too. But he wrote an excellent and very impenetrable paper about how feedback works, and that was the first sort of time that a line was drawn and said, okay, this is how it ought to be, as opposed to, we'll have a bit of a guess and see what happens. And what it boils down to is this block on the slide, where we've got an input VI, which enters into a block which subtracts one signal from another. Don't worry about whether they're voltage or currents, just think of them as signals. If you want to attribute something to them, just call it A sine X or T or whatever. And it will subtract the value of HVO. So we have an output as well, and we will have some block here which does something to the output, oftentimes makes it smaller. So you can think about it as a dividing thing if you want to, or multiplying or whatever. So we'll do H to VO, and we'll subtract that from whatever we had originally. And what we'll end up with here is an error term, which will be the difference between what we put in and H times our output. And this lot will get multiplied by whatever happens in G. So this could be times 1,000, this could be divided by 10, in which case this is bigger than that. I don't expect you to see where that came from, but by the end of the analysis you will probably agree. So the output voltage is VO, and a portion of the output HVO is fed back to the input. And this portion is subtracted from VI, leaving an error term, VI minus HVO, at the input of the gain stage G. And we can use this to model our op-amp, which is why it's significant. In fact, we can write out an equation that says VO is G, which is our forward path gain, which is why I call it G, times our input minus the error term. Or we can jiggle that to get V out over V in, which is the gain of our op-amp, and it turns out it's G over 1 plus G times H. And you can think of G and H as having frequency-dependent properties if you want to, but I don't expect you to do that in this course. It will come eventually, but not yet. We will think of them as being made up of resistors and gains and nothing else. And if G is very large, then G times H is much, much bigger than 1. So you can approximate, basically the 1 disappears and you end up with G over GH, and the G's cancel, which leaves you with 1 over H, which is really handy because now you've got this feedback system in which the output is controlled by whatever H is, and H is something that we will set with resistors. So we'll know what its value is going to be because we'll be able to measure the resistors or look at the draw they came out if we're feeling brave or lucky. So this is quite good for us because it means we can make an amplifier of a particular gain, with particular characteristics, without having to worry too much about what goes on inside our analog building block. I think we'll leave it there for now, and we'll carry this on tomorrow.